All right, so these are just a couple of last problems from the from class. So this is the problem on slide 17 from the final review from the pear deck that y'all are looking at. But basically, we need to determine the components of the support reactions at the fixed support A on the cantilever beam. So I'm just going to draw a quick free body diagram. And we have a force here, 4 kilonewtons, and then we have a force here at the top, which is 6 kilonewtons. This is 1.5 meters, 1.5 meters, 1.5 meters. This angle here is 30 degrees. This angle here is 30 degrees. And then we remove that fixed support at A. So we get moment about A, we get an AX and an AY. I just took a guess at which direction those are in. And I think that should be about it. So this is a static equilibrium problem. So what we can do is we can just sum the forces. So the equation we have is sum the forces in the x direction, the y direction, and the moments about a point. So I'm going to sum the forces in the x direction are equal to 0. And so for that, oh yeah, we need to mark what our positive and x, y directions are. So we get negative ax plus 4 kilonewtons times the cosine of 30 degrees. And then that 6 kilonewton force is just straight, is up and down, and AY doesn't count. So those equal 0. So AX equals that 4 times cosine of 30, which equals 3.464 kilonewtons. So that's one of the things we need. We can sum the forces in the y direction. So we get AY minus 6 kilonewtons minus 4 kilonewtons sine of 30 degrees. That equals 0. And so we get AY equals 8 kilonewtons. And then the last thing we need to find is that moment about A. So the sum of the moments about A equals 0. So for the sum of the moments about A, we have that M sub A is 1. That's in the positive direction. And then minus that 6 kilonewtons times 1.5 meters. Minus, and then I'm just going to break this 4 kilonewton force down into its 2 component forces. So just like we did for that earlier problem. So the x component is going to be 4 cosine of 30 degrees, that's kilonewtons. And then the y component is, let's see, right there, 4 sine 30 degrees kilonewtons. And so if we take that x component, it's going to give us a negative moment, but we do that 4 cosine of 30 degrees times that that perpendicular distance to A, which would be that 1.5 times the sine of 30. So this is just this distance right here. Use a different color. And that's just that 1.5 meters times the sine of 30. And then also this distance here will just be 1.5 cosine of 30 degrees. So we got that one, and then also that y component, which will also create a negative moment, so minus that 4 sine of 30 degrees, and then we want that x distance, so that's going to equal 1.5 meters plus 1.5 plus that 1.5 cosine of 30 degrees. And now I'm going to calculate this all out. So that all equals 0. So the moment about A equals 20.2 Newton meters. And so then I'd pick that direction was right, so that would give us this counterclockwise. So those are the 3 answers for that one. Then the next one is slide 18, and we're supposed to draw 2 lines on the zero force members in the truss. And so with this one, we've got this truss system. Let's see. Let's see. This highlighter is sort of a weird tool. I'm not used to using this for drawing. Let's see, we've got 3 kilonewton force here. We have E, so I'm going to say we have a EX and an EY. And then A is rollers, but we're just going to be A in the X direction. And you wouldn't have to draw out the free body diagram for this one, because all I was asking for is zero force members. So the 2 zero force members would be here and here. Let's see, I actually was missing one of the truss members. So we have those 2 zero force members. And then it's okay that I went ahead and started writing out some of this because of the next problem. I guess I may as well go ahead and finish it. Let's see. I'm putting in some of the dimensions, so 1.5 meters, and then this is 2 meters. And so for the next one, we're supposed to draw the free body diagram of joint A. So joint A, so we have A, we have AX, AB, and AE. These are all horizontal or vertical, so we don't need to draw any like angles or anything on there. And that's basically it for the free body diagram. There weren't any other forces applied to it, so that's it for that one. And then for the last one, it says this is slide 20, it says assume that you solve for the reaction forces and found that A sub x equals 4 kilonewtons. Using the free body diagram you drew for joint A and this value for AX, determine the forces in AE and AB. Indicate if these are in compression or tension with a C or a T. So AX equals 4 kilonewtons. So if we sum the forces in the X direction equal to 0, we get 4 kilonewtons plus AB equals 0. So we get AB equals negative 4 kilonewtons, which that means it equals 4 kilonewtons in compression. And then for AE, or the next one, we can sum the forces in the Y direction equals 0. So we just get AE equals 0 kilonewtons. So that wouldn't really be compression or tension. So AB and then AE. So that's through slide 20. Slide 21 is this big truss system. And for this one, they want us to determine the forces, or we're supposed to find the forces in members KJ, KD, and CD. And I wanted you to draw the free body diagram of the section that you're going to analyze. So remember with this, you're going to make the cut through those three members if you can, which with this one you can. So you want to cut through KJ, KD, and CD. And so I'm just going to start do the free body diagram now for that one. So we have, let's see, we have A, L, K, C. I'm just drawing that section. And then KJ is one of them that we would need to find. KD and CD. And the KD is going down 3 meters and over 2. So down 3 and over 2. So it's 3 and 2. And the square root of 3 squared plus 2 squared, which would be 9 plus 4, so square root of 13. So that's if we use the common triangles, that'll help us with that. And then just writing in the other dimensions, so 2 meters. The height of the truss system is 3 meters. And we would need to say what positive x and positive y is. But that would be our free body diagram. Then for the next question, or actually, no, we're missing something. So with A, we also have some forces at A for that the reaction forces. So we have AX and AY. And then for the next one on slide 22, we had found that AX equals, or we're given that AX equals 0 kilonewtons and AY equals 56.67 kilonewtons, and it has the arrow pointed up, so that means I drew it right on here. And we're supposed to find the forces in member KJ. Okay, so we're supposed to find this one here. You could find the other KD and CD also, but we just need to find KJ. So let's see, what do we want to do here? With this one, we can sum the forces in the y direction, because we can sum the moments about point C, but we have two unknowns, KJ and KD. So we can also sum the forces in the y direction to get to that KD. So sum of the forces in the y direction, we get AY minus that y component of KD. That equals 0, and AY was 56.67 kilonewtons. That equals KD times the square root of 13 over 3. So I'm just moving stuff over. So KD equals 56.67. Oh, wait a second. Oh, I totally messed up. So I messed up. So what I messed up with is I forgot to put, I just looked up at the free body diagram. I was missing some forces. So we had a force right here from point B, which is 20 kilonewtons. And then at point C, we had another force, which was 30 kilonewtons. So I'm just gonna erase, let's see, erase some of this. So we have AY minus that KD, that Y component of KD, and then we also have that 20 kilonewtons, so minus 20 kilonewtons, and then minus 30 kilonewtons. And that equals 0. And AY was the 56.67. So minus 20 minus 30 equals KD times 3 over square root of 13. So then we can multiply that out and we get KD equals 8.05 kilonewtons. So that means that I was right and it is in tension. And then we're supposed to be finding KJ is what we're interested in. So now that we have KD, we can figure out KG, so we can go back to that. I can sum the moments about C equals 0. And if we do that, yeah, I think that'll work. So sum the moments about point C equals 0. And we'll do coming out of the board is positive. So AY is going to create a negative moment. So negative 56.67 times 4 meters. Then plus that 20 kilonewton force. I'm not writing the units in. 20 kilonewtons times 2 meters. 30 kilonewton force is on C, so it doesn't create a moment. CD is also at point C, so it doesn't create a moment. And then if we go up to KD, that Y component of KD isn't going to create a moment, but the X component will, and it'll create a negative moment. So, oops, minus KD times 2 over the square root of 13. So it's just that X component of KD times 3 meters. And then minus, and that KJ times that 3 meters. That equals 0. And then we already found KD. So KD was this. So now we can multiply that all out. And let's see what we get. So I'm actually going to put the KD in here. 8.05. So I'm just opening my calculator. And I get KJ equals 66.7 kilonewtons. I'm not sure if I did I think it's negative. Yeah. Negative 66.7 kilonewtons. And so that just tells us that KJ equals 66.7 kilonewtons in compression. And that's what that had asked us for. So now the next one is just a ball is thrown vertically in the air. I feel like y'all have done pretty well with these problems. A ball is thrown vertically upward with a speed of 15 meters per second. Determine the time of flight when it returns to its original position. So then you just look at the equations that we have. So let's see, we know the initial velocity, we know the acceleration due to gravity, we don't know the time, that's what we're looking for. So if we look at the equations, the one that'll help us with this is we have S equals S naught plus V naught times T plus 1/2 A sub C times T squared. And it starts and ends at the same place, so let's just go to 0. So we end up getting 0 equals, that initial velocity is 15 meters per second, and we're doing up is positive, times time, plus 1/2, and then the acceleration due to gravity would be negative 9.81 meters per second squared, times time squared. So 0 equals t times 15 minus 4.905 t. So time equals 0 or 3.06 seconds. So time 3.06 seconds is when it'll return back to your hand, or to the original position. Cool. And then the next one on slide 24 is we have this conveyor belt that's moving at 4 meters per second. The coefficient of static friction between the conveyor and the 10 kilogram package B is mu sub s equals 0.2. Draw the free body diagram and kinetic diagram in your notes. So a free body diagram, that's the one that we're used to doing. So we have, let's see, the weight of it, which is 10 kilograms times 9.81 meters per second squared. So that equals 98.1 newtons. And then we have the force of friction, which is going to be the opposite of the direction that it will start moving. And then we have the normal force. So that's the free body diagram. Let's move this up. And then we have the kinetic diagram, which is just the crate again. And that point G, and then we just have mass times acceleration of the crate. So that's the free body diagram and the kinetic diagram. Excuse me. And then so that's it for that one. And then the last slide, slide 25, as it says the conveyor belt's moving at 4 meters per second. So the initial velocity is 4 meters per second, and it's moving to the left. If the coefficient of static friction between the conveyor and the package is mu sub s equals 0.2, so the mass of the package equals 10 kilograms. They want us to find the shortest time the belt can stop so that the package does not slide. So shortest time. So first we need to figure out what, so we drew our free body diagram, but we didn't figure out what that force of friction and what the N is. So we're gonna just sum the forces in the y direction equal to 0. So that'll give us N minus 98.1 newtons equals 0. So N equals 98.1 newtons. The force of friction equals mu sub s times N. So that equals 0.2 times that 98.1 newtons. So that's 19.62 newtons. And so that's the force of friction. Now we need to, to figure out what that acceleration is, or what that maximum acceleration is. So if we sum the forces in the x direction, that equals mass times acceleration. And the forces in the x direction is just that force of friction. So that's that 19.62 newtons equals the mass, which is 10 kilograms, times acceleration. And how I got this equation here was just from looking up here at the free body diagram, because you said that equal to the kinetic diagram. And so we have this, and then we get the acceleration equals 1.962 meters per second squared. And so now we know we have the initial velocity. The final velocity is just going to be 0. And we have the acceleration, we just need the time. So now we can go back to our kinematics equation. So v sub f equals v naught plus the constant acceleration times time. See, the final velocity is 0. So 0 equals, the initial velocity was to the left, so -4 meters per second, plus the acceleration was 1.962 meter per second squared times time. So time equals basically just that 4 divided by 1.962, which equals 2.04 seconds. So that's that solution to that last one. So that's the end of the final review.